In the last lecture, we have studied the concept of diagonalizable, whether the matrix is diagonalizable or not. So we'll see some more problems based on this concept. So let's have some more problems. Okay, so I hope all of you are able to see this Jamboard.
Yes, sir. Please send the link again.
Yeah. Okay. So we go for the example. Okay. Find the eigenvalues and eigenvectors for I hope you are able to see this matrix. Hence, find transforming matrix if it exists. Okay, so we have to find eigenvalues and eigenvectors for this matrix first. Okay, and if this matrix is diagonalizable, then only we can write the transforming matrix. Okay, so this is transforming matrix or model matrix or diagonalizing matrix. Okay, so finding the transforming matrix means checking whether this is diagonalizable or not. Because if this matrix is diagonalizable, then only we are able to find the transforming matrix. Okay, so let's go with the solution. Okay, so first we have to find out eigenvalue, eigenvectors anyhow. Okay, so what we'll be having, let A is equal to, so we have 2, 3, 4, 0, 2, minus 1, 0, 0, 1. Can any of you tell me what are the eigenvalues of this matrix and why? Can you find the eigenvalues without calculating? Any one of you, Minal? Can we have the eigenvalues of this matrix without calculating?
2, 2, 1.
Why?
So the determinant and sum of the diagonal. If we the sum is 5, so and the determinant is 4. If we divide that 5 to 2, 1, so we will get the eigenvalues.
Okay. So that is one reason, but again there is an easier way. You got is correct. Okay, whatever you said is correct. Okay, but there is one more result that I have given you. Okay, so using that, within a second you can say that what are the eigenvalues and why. Okay, see this is being upper triangular matrix. Okay, so this is a triangular matrix and we know the eigenvalues of the triangular matrix are nothing but the diagonal elements. Okay, so this comment I have given you as a property of eigenvalues. Okay, and this kind of properties should be used in the competitive examinations. So this eigenvalue, eigenvectors is a compulsory topic in GATE for every branch. Okay, and hence the question can be asked, what are the eigenvalues, or what is the sum of the eigenvalues, or what is the product of the eigenvalues. Okay, so we can just able to find out by looking at the matrix only. As this matrix has a property, it is upper triangular matrix, so we can directly say that diagonal elements are going to be the eigenvalues, and we can find out either sum or the product. Okay, and even we can find out the determinant as a product of diagonal elements. Okay, so we got here determinant is going to be 4. Okay, now we have to find out the characteristic equation. So now consider characteristic equation of A. So what is the characteristic equation? A minus lambda I is equal to 0. Don't be in hurry. You have to write everything properly. Okay, so determinant of A minus lambda I is equal to 0. Okay, and hence,
Sir,
what do you
can
have
you
here?
send Jamboard link?
Yes?
Jamboard link can you send?
See,
Sir, I have
one more
joined.
thing. Yeah, one more thing you need to understand. Jamboard link is always sent in the chat box, or you can find the Jamboard link to your mail ID also, through which you are logging in. Okay, so you can find that link twice or at 2 places. Okay, so I have again posted it, so you can see it. Okay, so now we can have the determinant of A is going to be 4. So we have to consider the characteristic equation. Always write the equation determinant of A minus lambda I is equal to 0. Then write the determinant, okay, 0, 2 minus lambda, and this is minus 1. Okay, and 0, 0, 1 minus lambda. Don't be in hurry. Okay. See, in competitive examination, you don't have to write everything, but in traditional examinations, you must write everything. Okay, so here we have to write this all. Okay, and then directly you can have lambda cube. Okay, minus 5 lambda square. Okay, what you have the next plus lambda, the minor for this 2. Okay, what will be the minor for this 2? You can have, this is going to be 2 minus 0 plus the minor for this 2. Again, you will be having this 2 minus 0. Okay, plus the minor for this 1. So 2 2s are 4 minus 0 and minus determinant. Okay, so what is the determinant we have? Minus 4 is equal to 0. So lambda cube minus 5 lambda square plus 8 lambda minus 4 is equal to 0. And you know the factorization, lambda minus 1, lambda minus 2 bracket square is equal to 0. So lambda is equal to 1, 2, 2. This is the repeated eigenvalue, so you must write it here. Okay, and hence what will be having? We can say the eigenvalues are, what are the eigenvalues? 1, 2, 2. Okay, once you know the eigenvalues, okay, and we have to check whether this matrix is going to be diagonalizable or not. So if I want to prove or check whether this is diagonalizable or not, then we must write the algebraic multiplicity and the geometric multiplicity of the eigenvalue. So here we get which multiplicity, whether we get the geometric or algebraic multiplicity here. Which multiplicity we can identify from this? Chirag, which is the multiplicity you can identify from the characteristic equation?
The number of non-zero geometric multiplicity.
Here we identify geometric multiplicity.
Yes, sir.
Dharmesh, Vinal,
Sir, I think it would be algebraic multiplicity.
right? It is algebraic multiplicity that we identify from here. Okay, so from characteristic equation we can identify the algebraic multiplicity. Geometric multiplicity is related to vectors. Number of vectors is the geometric multiplicity. Number of times this eigenvalue is repeated, that means this index is going to be the algebraic multiplicity. So here the algebraic multiplicity of 1 is going to be 1. The algebraic multiplicity of 2 is going to be 2. Or here you can see how many times this 1 is repeated, 1 time. So algebraic multiplicity is 1. How many times 2 is repeated? 2 times. So algebraic multiplicity is going to be 2. So from here we can identify algebraic multiplicity, and hence we can write the algebraic multiplicity of lambda is equal to 1 is 1, and the algebraic multiplicity of lambda is equal to 2 is 2. Okay, so 2 is repeated 2 times, 1 is repeated 1 time. Okay, so these are the algebraic multiplicities. Now if they have the same geometric multiplicity, then we can say the matrix is diagonalizable. And for having the geometric multiplicity, we need to find what are the eigenvalues corresponding to this eigenvalues. We have to find out the eigenvectors. So for lambda is equal to 1, okay, what we have a minus lambda I into x is equal to 0. Okay, so this is the system of linear equations that we have to solve. And here we have this lambda is going to be 1. So we have 1, 3, 4. You can see this matrix. So here I am going to put the value of lambda to be 1 now. So you're having 2 minus 1, 1, 3, 4, 1 minus 1. Okay, so you can have here 0, 1, minus 1 and 0, 0. So here it is already 1 and 1 minus 1 is going to be 0. Okay, so we can have here this is going to be x1, x2, x3, and here we can have this is 0, 0, 0. Okay, so how many distinct equations we have? How many distinct equations you can see here?
2 equations.
2 or 3? This is also
Two,
different.
sir.
No? Okay, so all 3 distinct equations we have. Okay, so can we apply Cramer's rule? Can we apply Cramer's rule here?
Yes, sir. Yes,
Yeah.
sir.
Because we need at least 2 distinct equations and we have 2, so we can use the Cramer's rule. We are always try to find the non-zero vectors. So we should not consider this 0 row. Okay, we should consider non-zero rows. Okay, and hence you can say by Cramer's rule. We have, okay, so what we'll be having here, x1 upon, we will be having this is 3, 1, 4 minus 1 is equal to minus x2, and we have here this is 1, 0, 4 minus 1, and this is equal to x3. Okay, we have 1, 0, 1, 0 and 1. Okay, so can you calculate this? Okay, what will be the determinant here?
Minus 7.
Minus 7.
Minus
7.
7. Okay, so minus x2. What is the determinant here?
Minus 1.
1.
Minus 1. Okay, and what is the determinant here?
1.
1.
1. Okay, so can we cancel this minus and we can have the vector? So what is the first vector we can have? So can I write this as 7 minus 1 minus 1? Because I am multiplying by minus. I don't want the first component to be negative. So I have multiplied the entire equation by minus. So is this okay?
Yes.
Okay. So is the eigenvector corresponding to eigenvalue lambda is equal to 1. So what is the geometric multiplicity of this eigenvalue? How many vectors are corresponding to lambda equal to 1? So we can have geometric multiplicity of lambda is equal to 1 is 1, because there is only one eigen vector corresponding to lambda is equal to 1. Okay. Now we have to think of the another eigenvalue. So for lambda is equal to 2, okay, we have, what will be having, again you have to write the same equation, a minus lambda I into x is equal to 0. Okay. So what we get here now, this lambda is equal to 2. So 2 minus 2 is 0. This is 3, 4, 0, 0, minus 1. And this is 0, 0, minus 1. Okay. And here we have x1, x2, x3. And then we have here, this is 0, 0, 0. So you can see here, if I put lambda is equal to 2, then this will be 0, 3, 4. This will be 0, 0, minus 1. This is 0, 0, 1 minus 2. 1 minus 2 is going to be minus 1. Okay, and that's how we have got this equation. Okay, so how many distinct equations we have? How many distinct equations we have?
2.
Which two equations we have?
First and second. Or first and third.
Second, because second and third is going to be same. Okay, so we cannot consider this as the distinct equation. So what we have to do to find out the eigenvector? Kiran, what we have to do to find out the eigenvector? Pawan, what we have to do to find the eigenvector for this?
Cramer's rule, sir.
Cramer's rule. So we have to apply Cramer's rule.
Cramer's
Good. Good. So we can say by Cramer's rule, we have, so what will get? x1. So if I want to apply the Cramer's rule, I have to choose the equations. Okay, so here without loss of generality, we consider the equation 1 and 2. So we can have x1 upon, if I consider for x1, then it will be 3, 4, 0, minus 1. And this is minus x2 upon what we have here. So this will be 0, 0. Then what we'll get here for x2, so this is 4 minus 1, and x3, what we'll be having for x3, so again this is 0, 0, and you can have 3, 0. So we can have x1 upon, so this is going to be minus 3 equal to minus x2 upon 0 is equal to x3 upon 0. So can I have this x2 like 1, 0, 0? Can we write like this? Can we write like this? X2 is equal to 1, 0, 0?
Yes, sir.
Because minus 3, I can divide everything by minus 3. Here it is 0, so I don't have any problem. Okay. And so we can write x2 is equal to 1, 0, 0. Okay. So we can have hence x2 equal to, okay, so it is going to be 1 0 0. Okay, so we got here this is going to be 1 0 0 is the eigenvector corresponding to eigenvalue lambda is equal to 2. So what is the geometric multiplicity of lambda is equal to 2?
1.
Because we have only one eigenvector, so the geometric multiplicity is 1. Okay, now we can see, okay, so whether we get the transforming matrix or not. Okay, we have considered the algebraic multiplicity, and we got the algebraic multiplicity here. Algebraic multiplicity of lambda 1 is equal to 1. Algebraic multiplicity of lambda is equal to 2 is 2. Then we got the geometric multiplicity of lambda is equal to 1 is 1. Okay, and here we are getting the geometric multiplicity of lambda is equal to 2 is 1. So does this satisfy the conditions of diagonalizability? What is the condition for a matrix
No,
to be
sir.
diagonalizable? What is the condition? Why not? Is this matrix diagonalizable?
Algebraic and geometric multiplicity should be same. So here it
Yes.
is not same.
Yes. Okay. So the condition for diagonalizability is the algebraic multiplicity and the geometric multiplicity of every eigenvalue must be same. Okay. But in this case, we are having the algebraic multiplicity and geometric multiplicity equal for the eigenvalue lambda is equal to 1. But for the eigenvalue lambda is equal to 2, we are having algebraic multiplicity 2 and geometric multiplicity 1, which is not equal. Okay, and hence we can say that the matrix is not diagonalizable. Okay, and if the matrix is not diagonalizable, we are not able to find the transforming matrix. Okay, so this way we have to write the answer for this question. Okay, so here we need to give the reason why it is not diagonalizable. Okay, and then we can say that hence transformation matrix does not exist. Okay, so here we can see since algebraic multiplicity of lambda equal to 2 is 2 and the geometric multiplicity of lambda is equal to 2 is 1. Okay, hence the given matrix is not diagonalizable. Okay, that is the transformation matrix, transforming matrix does not exist. Okay, so see, what was the question given to you? The question was find eigenvalues and eigenvectors. Okay, so first part is find the values of eigenvalues and eigenvectors for the matrix, and hence find transforming matrix if it exists. Okay, so if it exists, then we have to find. Okay, but we proved that it is not existing. Okay, because the algebraic multiplicity and geometric multiplicity are different for the eigenvalue lambda is equal to 2. So we cannot have the transforming matrix, and we cannot have this matrix to be diagonalizable. Okay, so is there any doubt in this question? Is there any doubt in this question?
No, sir.
Okay, all of you got the solution. Rajat, is there any doubt?
No, sir.
Nancy, is there any doubt?
No, sir.
Okay. So all of you got the answer for this question?
Yes, sir.
Yes, sir.
Sakshi? Sakshi, you got answer? Okay. So now we'll go for the another question. Okay. So let us go for the another question. Okay, write down the question. Find the diagonal form and model matrix for A is equal to 221 131 127 if it exists. So we have to go through the solution. So to prove the existence of this model matrix, always we have to find out the eigenvalue and eigenvectors. Okay, so sometimes the question may be as previous, find eigenvalue and eigenvectors and then find, or sometimes the question will be like this. Okay, and this condition is always there if it exists. So if the matrix is diagonalizable, then only this will exist. If the matrix is not diagonalizable, then the model matrix or the transforming matrix will not exist. So we have let A is equal to 2, 2, 1, 1, 3, 1, 1, 2, 7. Okay. So this is the matrix. B, the given matrix. Then what we have to do first, consider determinant of A. So 2, 2, 1, 1, 3, 1, 1, 2, 7. So calculate the value of the determinant. Now we have, so what we have, characteristic equation of A as, so it is determinant of A minus lambda I is equal to 0, and hence here you have 2 minus lambda 2 1 1 3 minus lambda 1, and I'm having 1 2 7 minus lambda is equal to 0. What is the value of the determinant? Any one of you have got it?
25.
25. Please confirm others. Is that okay?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So the sum is going to be 12 and the product is going to be 25. What are the eigenvalues? The sum is going to be 12 and the product is going to be 25. So what are the eigenvalues?
5 into 5 into 1 into 1.
But is that
237.
no 237? How it can be 237? Okay, so it will be complex one. Okay, so let us make it simple. Okay, make this entry 2. It will be more easy because it will be complex then. Okay, so we don't want to go to complex.
Sir, it's coming in quadratic form.
Yeah, that's why I said let us make it more simple. And I can change one entry and make it simple. So now see, it will be more easy. What is the value of the determinant now?
115. Eigenvalues.
Determinant, what will be determinant? 5. If 115 is your eigenvalues, then the determinant will be 5, no?
Yes, sir.
Yeah. So we can have 5 and then 7, so 115, yep. Okay. And then we can have, this is lambda cube minus how many, what will be having here? So it is 7 lambda square plus what is the product, sum of the minors? Lambda minus 5 is equal to 0. So lambda minus 1 bracket square, lambda minus 5, that is equal to 0. What this sum is? What is the characteristic equation you are getting? Lambda cube minus 7 lambda square plus what this term is? You have got this value, no?
11, sir.
11 plus 11, right? Okay.
Yes.
So this is 11. And you can have now, so you can say that lambda is equal to 115. Okay, so we can say the eigenvalues are lambda is equal to 115. So can you tell me what is the algebraic multiplicity of lambda is equal to 1 and algebraic multiplicity of lambda is equal to 5? So what is the algebraic multiplicity of lambda is equal to 1? How many times it is repeated?
2 times.
2 times. How many times 5 is repeated?
1 time.
1 time. So we can have algebraic multiplicity of lambda is equal to 1 is 2, and then algebraic multiplicity of lambda is equal to 5 is 1. Okay, so here we got the algebraic multiplicities. Now we have to find out the geometric multiplicities. So for lambda is equal to 1, we have, what will be having? A minus lambda I into x is equal to 0. So here we have to consider. So lambda is going to be 1. We can have this 2 minus 1. So we'll be having 1, 2, 1. Okay, so this is going to be 1, 2, 1. This is 1, 2, 1. And now again you will be having 1, 2, 1. Okay, and here we got x1, x2, x3, and this is equal to 0, 0, 0. So are you getting these equations? Are you getting these equations? Because I have put the value of lambda is equal to 1 now. So the first equation is 1 to 1, second equation is 1 to 1, third equation is 1 to 1. So how many distinct equations we have?
One.
We have only one distinct equation. So we can say we have x1 plus 2x2 plus x3 is equal to 0. So is the Cramer's rule applicable here?
No, sir.
No. Okay, because we have only one equation, so Cramer's rule is not applicable. And when Cramer's rule is not applicable, we have to solve this equation 2 times. Okay, so what we'll do, we'll consider case 1. Okay, so in case 1, I assume that the third dimension is 0. That means I assume only xy plane. So x3 is equal to 0, and hence what you got is x1 plus 2x2 is equal to 0. So I can write x2 is equal to minus of x1 by 2. Okay, so what I can do is put x1. So the value of x1 we have to put in such a way that it should be positive, okay, and x2 should be integer. So what minimum value you can put? See, this is the equation that we have to solve. Okay, so we have to choose the value of x1, which is minimum positive integer, so that the x2 will be integer. What value you
Minus
can?
2.
Minus 2. What if I put 2?
It will be minus, then x2 will be minus.
This will be minus 1, no? If I put x1 is equal to 2, okay, then we have x2 is equal to minus 1. And this already we have assumed 0. So if I put x2 is equal to 2, this is an integer, so x2 is equal to minus 1. And x3 we have already assumed that it is equal to 0. Now we have to consider the next case. So here what we assume is let x2 is equal to 0. So you got x1 plus x3 is equal to 0. And hence what we get here, x3 is equal to minus x1. So we have to put the value of x1 such that the value of x3 will be integer, and hence you will be having the next eigenvector. So we'll have here, what is the eigenvector you can have, and what is the value of x1 you can choose. What value of x1 you can choose, so that the x3 will be integer, but x1 should be a positive integer. What value we can choose? Easily, if I choose this, this will become minus 1. So 1, 2 already we have said 0, and x3 is minus 1. Hence here, what we got here, so x1 is equal to 2 minus 1, 0, and x2 is equal to 1, 0, minus 1 are the eigenvectors corresponding to eigenvalue lambda is equal to 1. Okay, and hence what is the geometric multiplicity of lambda is equal to 1? How many eigenvectors corresponding to lambda is equal to 1?
2.
2. So geometric multiplicity is 2. Okay, so number of eigenvectors corresponding to the eigenvalue is the geometric multiplicity. Now we have to think for lambda is equal to 5. Again, same steps we have to follow. So we have a minus lambda I into x is equal to 0. So here we have This is 2 minus 5 minus 3, and you can have this 2 1. Okay, so we'll be having here these entries will not change, so it will be 2 1. Then this is 1. Okay, so we got here 3 minus 5, so we'll have minus 2, and this one remains here. Okay, then this is 1 2 will be there, and 2 minus 5. Okay, so 1 2 will be there, and this will be minus 3. And here we have x1 x2 x3. So this is equal to 0 0 0. Okay, now how many distinct equations we have here? How
3.
many distinct equations we have? 3. So what we will do to find the eigenvector? What we'll do?
Take any two equations.
Yeah.
Take any two of from them.
Take any two. So we'll use Cramer's rule, right? Okay. So by Cramer's rule, we have. Okay. So which two rows you want to take? Without loss of generality, first, second, or second, third? We always have chosen first and second. Now we'll choose second and third. Let us see. Okay. So what we got here? Hence x1. Okay. So x1 you'll be having minus 2 to 1 minus 3. So this is minus 2 to 1 minus 3 is equal to minus x. And here we have 1 minus 3 remains as it is. So here you'll be having 1 1. So this is 1 1. And this is equal to x3. So we got here 1 1 and minus 2 2. Okay, so that's what we have. Now simplify this. So we can have x1. What is the determinant value of this?
4.
4. How? So this will be 6 minus 2, 4, right? Minus x2. What is the determinant value here?
4.
4 or minus 4? What about this thing? Again, it is going to be 4. So we can see that x3 is equal to 4. You can cancel throughout, and you will having the eigenvector like this. Okay. So this is the eigenvector we have. So is the eigenvector corresponding to eigenvalue lambda is equal to 5, and hence what we can say is geometric multiplicity of lambda is equal to 5 is going to be 1. Okay, so once you know the geometric multiplicity of this eigenvalue, okay, and now you need to check. Okay, so the question is the given matrix diagonalizable? Because we have calculated the eigenvalues now, we have calculated the eigenvectors now. Okay, so you have the algebraic multiplicity, you have the geometric multiplicity. Now you need to take the decision. So tell me, what do you think?
It is
It is diagonalizable.
Is it so?
yes.
Yes, sir.
Yes, sir. It is.
Okay. Why you can conclude that it is diagonalizable matrix?
Because algebraic multiplicity and geometric is the same.
Yes. Okay. So when we consider this matrix, we can see that the geometric multiplicity and the algebraic multiplicity of every eigenvalue is going to be same. Okay. So the geometric multiplicity of lambda is equal to 2 is 2. Lambda is equal to 1 is 2. Algebraic multiplicity of lambda is equal to 1 is also 2. So we can say the geometric multiplicity and the algebraic multiplicity is same. In case of the eigenvalue lambda is equal to 5, it is also the geometric multiplicity is 1 and the algebraic multiplicity is 1. Okay, so we can have the geometric multiplicity equal to the algebraic multiplicity for every eigenvalue. Okay, and hence this matrix is a diagonalizable matrix. Okay, so we can say here, since algebraic multiplicity of lambda I is equal to geometric multiplicity of lambda I for I is equal to 1, 2, 3. Okay, hence the given matrix A is diagonalizable. Okay, so if it is diagonalizable, then we have to write the diagonal form and the transforming matrix. Okay, and hence we have, okay, so D for the diagonal form 1 0 0 0 1 0 0 0 5, and we have diagonal form of A as, and the model matrix is M is equal to, okay, so the first eigenvector that we have calculated, so it is 2 minus 1 0. Okay, so it is 2 minus 1 0, 1 0 minus 1, and the latest one we have calculated is 1 1 1. So this is 1 1 1. So you can see that this column corresponds to lambda 1, this column corresponds to lambda 2, this column corresponds to lambda 3. So this is your first vector, this is your second vector, and this is your third vector. So you must write the corresponding eigenvalues and eigenvectors. As the order you follow in D, the same order you should follow in M. Okay, and if the order is not followed, then this M will not be invertible. Okay, and if M is not invertible, then you cannot have this diagonal form. Okay, so that's why we have to be very careful. Okay, so here we have seen the diagonalizable matrices and non-diagonalizable matrices. Okay, so we have considered the matrices with repeated eigenvalues. Okay, one thing you need to understand, the matrix is always diagonalizable. Okay, so write down this comment. Okay, so this is the important result, you can say. Okay, this is noted. The matrix with distinct eigenvalue is always diagonalizable. Okay, so the matrix with distinct eigenvalue is always diagonalizable. Okay, so we don't have to worry about the matrix with the distinct eigenvalue. We have to worry about the matrix with the repeated eigenvalue. So in case of repeated eigenvalue, if you find the algebraic multiplicity is same as the geometric multiplicity, then yes, you can say it is going to be diagonalizable. And if it is not followed, then you can say that it is not diagonalizable. Okay, so is there any doubt in this concept now, diagonalizability?
No, sir.
No, sir.
Okay, that's good.